Okay, here RT, we find RT derivative. So this will be a cosine. So cosine will be negative sine. So we get negative a sine t, and then a cosine t. Its t derivative is 1. So the unit tangent vector will be, so define the unit tangent vector. So RT derivative absolute value norm. So this will be negative a sine t squared, norm of a vector a cosine t squared plus 1 squared. Take square root. So you get this is sine squared plus cosine squared. We get 1. So it's a squared plus 1. Okay, so then you see tangent vector, unit tangent vector will be tangent vector over its norm. Tangent vector over its norm. So this will be, the norm is constant, a squared plus 1. Okay, so this is actually negative a sine t, negative, so it's a cosine t, 1. So we find the curvature kappa at t. This will be this norm tangent vector derivative over tangent vector norm. Okay, the tangent vector derivative, what we get is, so you see here, t derivative will be 1 over square root a squared plus 1. So here we have negative a cosine t. This is negative a sine t. 1 derivative 0. So the norm of t derivative will be, you see, you get this is, now factor out this scalar factor times this norm, negative a cosine t squared plus negative a sine t squared. Okay, so you get this is a over square root a squared plus 1, which is the norm of the unit t derivative. Okay, so t derivative will be a over square root a plus 1. Now tangent vector norm, we get this is square root a squared plus 1. So finally we get this is a over a squared plus 1. A over a squared plus 1. So the helix kappa t is a over a squared plus 1. Okay, so you see this is less than 1 over a. Less than, if you divide by a, so it's the a plus 1 over a. This is less than 1 over a. Okay. So you see the helix, the curvature of a helix is smaller than that of a circle, although they have the same radius. Okay, it makes sense. Okay, because the helix has a motion along the z direction, has a motion of the z direction. So although the direction change is the same, but the arc length becomes longer. Okay. So the curvature should be smaller. Okay, now next we give a form of a curvature in general parameter t. Okay, in general parameter t. So theorem proves that the curvature of a vector function RT. So the curvature of the curve R equals RT. Now this curve is given by this vector function. Is, so this kappa t, which is R first derivative, cross product R second derivative, divided by R derivative cubed. This take absolute value, take a norm, so it's a scalar. Now we give a proof. Now we give a proof. Okay. So remember, kappa t, we already find its form, which is tangent vector derivative over tangent vector norm. Okay. Where tangent vector t, capital T, tangent vector. So this is tangent vector over its norm. Okay, tangent vector over its norm. And then now we actually prove this. Prove. Now we give a proof. Okay, then we have this will be so we change a little bit. So this gamma derivative r derivative at t. So this will be tangent vector times the norm. Okay, this will be tangent vector at t times ds over dt. ds over dt. Okay, now if we take derivative, second derivative at t, so this will be this tangent vector by product rule, okay, by product rule, plus tangent vector dot product times this will be d squared s over dt squared. Remember, remember, tangent vector at t is unit vector. It's unit vector. Okay, it's unit vector. That's unit vector equals 1 because unit vector is a unit vector. Unit vector. So unit vector has constant norm, which means its derivative will be perpendicular. So its derivative will be perpendicular. It's orthogonal. It's orthogonal to tangent vector. It's orthogonal to capital T. Okay, so we can do cross product. Okay, do cross product. So lead our derivative cross product are second derivative T. Okay, remember T and T, they are T and T. Cross product T cross T, we get a 0. Okay, a vector cross product with itself is 0. Okay. Okay, by the linear property, we can actually get this should be we can get this thing should be so we have okay now substitute. So this is T capital T ds over dt cross product with T derivative ds over dt plus capital T d squared s over dt squared. Now remember, see T and T, they are same parallel, the same parallel direction. Cross product of the thing, we get a 0. Okay, so we actually get this parallel terms vanishes when we do cross product. So we get this is T capital T cross capital T derivative times ds over dt squared. Okay. Okay. Then we have. Okay, you see, this thing also value. This is actually ds over dt. Okay. So finally, you see this norm cross our second derivative norm over this thing to the power 3. This will be exactly We already know. Okay. Now this is a perpendicular. Okay, perpendicular. ds over dt squared over now this gamma lambda our derivative as norm. Its norm is ds over dt cube. Okay. Now remember, tangent vector and its derivative, they are orthogonal. So the norm of their cross product is, so the angle between them is 90 degrees. So this is the cross product of their norm is norm of their product of their norms. Okay. Now ds over dt squared cancel a square factor there. So this will be ds over dt to the power 1. Okay, to the power 1. Okay. So remember, we last step is ts. The tangent vector is unit vector. Okay, unit vector in variable s, or in variable s or variable t, whatever. Sorry, it should be everything should be in t. Sorry, t. Wait a second. This should be t. This should be t. This should be t. Okay, this should be t. This should be t. Okay, this thing in variable t, tangent vector, capital T is unit vector. Okay, so we get this is its norm is 1. So we get a capital derivative, capital T derivative, norm over ds over dt. Remember, ds over dt is exactly our derivative. Okay, so this is exactly our definition of. This is our exactly the definition. Okay. This is exactly the definition of curvature. Let's see. We have our definition. You see? We have our definition of a curvature. Okay. So this, you see, this is one definition. Okay, this is one definition. We have several different definitions of curvature. Okay. And you see what we finally get. Okay, so you see this form, we again recover the thing again. Okay, so we are done. Okay, so we are done. So we have a formula to compute a kappa curvature. Okay, compute curvature of a curve. Okay, now let's try to find a plane curve. Plane curve. Okay, let's find a plane curve on the xy plane. Okay, so we will use this thing. Use this formula to derive an expression for curvature. Okay, suppose we have a curve y equals fx. Okay, suppose we have a graph of a function y equals fx, and we want to find the curvature of this function. Okay. Okay. Suppose we want to find the curvature of a graph. Okay. Suppose we have a function y equals fx for a plane curve. For a plane curve, y equals fx. Now this is a graph of a function. Now how do we find the curvature? How do we find its curvature? How do we find its curvature? We can write this thing as we can choose variable as x. Okay, we can choose variable x. So we can find r. Okay, so if you have a graph, y equals fx, x, y. So the vector you can choose r, x. So x coordinate is that's the x. Y coordinate is fx. Okay, so we get the vector form. And then so we need to use this. Remember r kappa at x. Kappa at x is r derivative with respect to x cross product with r second derivative. Norm divided by r derivative to the power norm to the power 3. Okay. Now we use this to compute it. So r derivative is x derivative. Now we are taking derivative with respect to x, wherever x. Okay. R derivative is y f derivative. Okay. Our second derivative. Now we are taking derivative with respect to x. Y derivative is 0. Second derivative is second derivative of f. Okay. So you see r cross our second derivative. You can use the ijk, okay, ijk. So this is y f derivative, 0, 0, 0, f second derivative. Now you see this should be, so if you expand ij, this will be 0. So the only non-zero is actually k. This y f second derivative, f derivative, 0. So this will be k times f second derivative. Okay. So the norm is exactly absolute value of second derivative of f. Okay. Second derivative of f. Okay. Then absolute value of the thing. Absolute value of the thing should be, now r derivative is y f derivative. So this will be, so look at r derivative. So we have r derivative in the red box, and then find its norm. Okay, find its norm. We have the component of a vector, and then we use Euclidean norm. So this is the y squared f derivative squared. Okay, f derivative squared. Okay, so you see this actually tells us so the kappa at x should be so this is the 1 plus f derivative squared to the power 1/2. This is the norm. So this should be the thing cross r second derivative of value over r derivative to the power 3. So rearrange everything. So we got this is the numerator is f second derivative of the value. Denominator is 1 plus f derivative squared to the power 3 over 2. Okay, 3 over 2. 3 over 2. Okay. All right. Now suppose we want a railway. Okay. Suppose, for instance, we need this structure of a railway. Okay. We need to design a railway. Now we want the curvature is small. Okay. You see if fx, example, if fx is x squared. Fx is x squared. It's graph. Now the curvature at let's see at 0. The curvature at 0. You see fx is x squared. Then you see what do we get? What we get is kappa at x is f second derivative norm over 1 plus first derivative squared to the power 3 over 2. Second derivative, you see this f second derivative. F derivative is 2x. F second derivative is 2. So it's 2 over 1 plus second derivative squared. So it's 4x squared to the power 3 over 2. Okay. So we can find the curvature. We can find the curvature at 0, 0. You see? At 0, this actually you see key maximum, curvature maximum. Maximum is when x is 0. Okay, when x is 0. So you see this is kappa at 0. So this is actually 2 over 1 plus 0, 0, 2. So this curvature is 2. Curvature is 2. Now you see the parabola. The parabola when x approaches infinity, the parabola is more or less looks like a straight line. Okay, straight line. You know, the curvature of a straight line should be reasonably, we think that thing should be 0. So you see, this agrees with our algebraic expression. So as x approaches infinity, plus minus infinity, so you see kappa x approaches 0. Okay, i.e. the parabola y equals x squared looks more or less looks like a straight line, more flatter. Okay. So the curvature is non-zero. Okay, you see the maximum curvature is non-zero, which is not a good thing. Because suppose you use the parabola, the curve of parabola, to design a railway, turn around a railway, turn the direction. Now, actually, this is not good choice because the curvature is non-zero. Okay. Then this can be dangerous if a train drives and turn around use on a quadratic curve. Okay, on quadratic parabola. Now you see if we fx be x cube. Now this curve looks like this. Now you see what happens at 0. So the kappa, you see, f derivative will be 3x squared. F second derivative will be 6x. Okay, so kappa x for this curve, for the cube, y equals x cube, this will be f second derivative of the value. So this will be 6x of the value over 1 plus f derivative squared. So it's 9x power 4 to the power 3 over 2. Okay, now this will be 6 of the value of x, 1 plus 9x squared power 3 over 2. You see, kappa minimum at 0. Kappa achieve minimum is you plug in x 0. You see, the numerator is 0, denominator non-zero. So kappa 0 is 0. So in this case, okay, the curvature is 0. Okay, curvature is 0. So in some sense, the curve x cube looks like more smooth. Okay, looks more smooth at 0 than the parabola at 0. Okay, so it's more looks like flat. So it's better if you turn the direction of a railway, use a degree 3 curve rather than degree 2 curve. Okay. Okay. Maybe one more example. one more example. Let's see this. Find the curvature of the curve y equals sine x. Example. Find the curvature of the curve y equals sine x at 0, 0 and pi over 2 y. Pi over 2 y. Okay. So remember, so fx is sine x. Then kappa at x. This will be second derivative norm, second of the value over 1 plus first derivative squared to the power 3 over 2. Okay, so at a 0, so here f derivative gives us sine derivative gives us cosine. Second derivative, take derivative cosine again, so we get negative sine x. Okay, so we get kappa at x for the sine curve. So this will be absolute value of this negative sine x over 1 plus cosine x squared to the whole thing to the power 3 over 2. Okay, so this will be sine x absolute value over 1 plus cosine squared 3 over 2. Now kappa at 0. Kappa at 0, you see this is actually 0. Sine 0. 1 plus cosine 0 squared 3 over 2. So this is actually 0. Okay, sine x. Okay. Why? Now the question is why sine x is actually curvature is 0 at 0. Remember we have the Taylor expansion. Remember Taylor expansion. Sine x equals x minus x cubed over 3 factorial plus higher order. Okay, you can so you can see locally sine x is really close to x. Okay, i.e. now the curve y equals x is a straight line. Okay, a straight line, and a straight line has curvature 0. Okay, straight line has a curvature 0 for sure. You can just use that formula to find. Straight line has curvature 0. Okay, now sine x can be its graph locally at a 0 can be approximated by a straight line. Okay, now the degree 3 curve sine x cubed. Remember x cubed is very smooth. The curvature of x cubed is actually 0. Okay, so the composition should be reasonably have curvature 0 at a 0. Okay, now of course degree 5, degree 7, etc. They converge fast. Okay, the curvature is also small. The curvature is also 0. So this explains why sine x has curvature 0. Okay, now how about curvature at pi over 2? Curvature at pi over 2. Then we get this is you plug in, you find that thing will be so this will be sine pi over 2 of the value. Sine pi over 2 is 1 plus cosine squared pi over 2 to the power 3 over 2. You plug in the value. Okay, this is actually 1 over 1 plus 0. 0, 2. So it's actually just 1. So the curvature at pi over 2 is 1 for this curve. Okay, now let's maybe talk about this. How do we so now not necessarily every curve we can write it as a graph of a function y equals fx. Now if we have a general thing parameterized by a parameter and two functions. Suppose we have this curve at y equals according now let's see what my notation is. Suppose we want to find a curvature of a plane curve, not necessarily a function with certain parameter. So suppose the parameterization is for a plane curve with parameterization x equals ft, y equals gt. Okay. Okay, it's maybe it's possible that it's very difficult to cancel the variable t to write y as a function of x or x as a function of t. Okay, so in this case, you see, we use this. We write rt, the vector rt as xt yt, so it's fg. Okay. So for some parameter t, okay. So we use kappa at t. Curvature is r derivative cross product r second derivative over r derivative norm to the power 3. Okay, so this is a formula for curvature. We already proved this. Okay, so r derivative is f derivative, g derivative. R second derivative is f derivative, second derivative, g second derivative. Okay, cross multiply. This will be f derivative, g derivative, cross multiply f second derivative, g second derivative. Okay. So cross multiply, actually we get this to be f multiply g second derivative minus g derivative times f second derivative. Okay. To the part, this to the direction key. Write down the determinant. Okay. Now if you take absolute value, so you get a r derivative cross multiply r second derivative absolute value. So this will be so this will be f derivative g second derivative minus g second derivative f second derivative absolute value. Okay, absolute value. Okay. Then r derivative norm. So this will be f derivative squared plus g derivative squared. Okay, I'll take a square root. Okay, so kappa t, this will be f derivative g second derivative minus g first derivative f second derivative over square root. Sorry, it's not to the power 3. Okay, so f derivative squared plus c derivative squared to the power 3 over 2. Now numerator take it absolute value. Okay, so this is the curvature of a curve in this parameterization. Okay. Now, for instance, curvature of an ellipse. Example. So x squared over a squared plus y squared over b squared is 1. So it's an ellipse. So this is an ellipse. Okay, maybe I just insert an ellipse, use a mouse. Okay, so this is an ellipse with okay, so this is an ellipse. Here, x-axis. Here we have y-axis. Now here, this is intersection is A. Here the intersection is B. Okay. Now we can use find a parameter t. So we can write x is a, let's see, cosine t. Y is a b sine t. Okay. Then we can find the curvature at t. So you see x derivative is, so t, we are taking derivative with respect to t. This a negative a sine t. Y derivative is b cosine t. Second derivative is a cosine t, negative. Y second derivative will be negative b sine t. Okay, so curvature at t. This will be x derivative y second derivative minus x second derivative y first derivative over x derivative squared y derivative squared is to the power 3 over 2. Take as value. So this will be plug it in, okay? Plug in. So this will be negative a sine t. Y second derivative, this will be negative b sine t. Minus x second derivative, so this will be negative a cosine t. Now y first derivative, b cosine t. B cosine t, also value. Over this is the a squared sine squared. B squared cosine squared to the power 3 over 2. Now the numerator is easier. Numerator you can factor out AB. Then you get sine squared plus cosine squared. So you get actually numerator is AB. Okay, numerator is AB. Then denominator is a squared sine squared t plus b squared cosine squared t to the power 3 over 2. Okay? Okay. So at 0, if t equals 0, then we get xy is a0. So this is the point. This is the point. Let me plot. Okay, a0. So this will be a0. Okay, so this is the x. So this is a0. So you see at a0, the curvature is the largest. The curvature is largest. Curvature is largest. So you get curvature at 0. So this will be AB. Plug in the formula. AB over sine t is 0. So we got a b squared cosine 0 is 1. 3 over 2. So we got this to be AB over b cubed. So we got a over b squared. Okay. So here a is greater than b. A is greater than b, we assume. At t equal pi over 2, then we get xy is the point 0b. Then the curvature will be kappa pi over 2. This will be b over a squared by symmetry. Okay, by symmetry. A or a split a with b. Okay, flip a with b. So we are done with the curvature of an ellipse. Okay. Now you see if a equals b, then remember if a equal b, then an ellipse will be a circle. Okay, will be a circle. Now curvature of a circle, this will be 1 over radius. The radius is a. Okay, a is radius of a circle. Now you see the curvature of the ellipse will be the curvature of the circle. Okay, 1 over a. You assume a equal to b, then actually you get a 1 over a or 1 over b. Okay, ab equal. Okay, so this will be radius of a circle. So this an ellipse is a circle is a special case of an ellipse. Okay, so we should get the case of a circle. Otherwise, it should be wrong. Okay. Now let's talk about curvature. Let's see. Okay, now the next topic. Let me see how long it takes. Okay, now let's start another topic, the normal and binormal vectors. Okay. Okay, the normal and binormal vectors. Binormal vectors. Normal and binormal vectors. Okay, suppose we have a tangent vector. Now, by tangent vector, we mean unit tangent vector. So, as we did before. So let capital T at T be a tangent vector. Be the tangent vector. Tangent vector to a curve. To a curve. Let's see, the curve is given by vector equation RT. Okay, now we already know. Note that since this tangent vector is unit vector, constant. Now for constant, remember constant vector, constant norm vector, then its derivative is perpendicular to this vector. So this actually we know we have tangent vector derivative is perpendicular to this thing. Now the normal vector, the normal direction is the direction perpendicular to the tangent direction. Okay, perpendicular to the tangent direction. Then we define the unit vector as the unit normal vector. Okay, so the normal direction is the direction perpendicular to the tangent direction. So if you, for instance, tangent direction, T. Okay, normal direction. So this T is tangent direction. Tangent vector. Now the normal vector. Now you see the normal vector has two directions, either inside or outside. Actually, we define this. The unit vector define this tangent direction derivative over its norm. This unit vector as the unit normal vector, as the unit normal vector. Unit normal vector. Now, for the curves that I plot on the right, now you see, actually, we use the inside normal vector. It pointing towards inside, okay, by the definition. You can find what T derivative is, okay? T derivative, T is actually, you see, T is, if you move to one point, you see this is the origin, T changes, rotate a little downward, okay, rotate a little downward. So actually, the unit vector, the normal vector is pointing towards inside, okay? So the normal vector, so we get it right, normal vector, unit normal vector is T derivative over its norm. Definition, okay? The binormal vector is defined as, using the right-hand rule, the binormal vector. Sorry. The binormal vector is defined as, okay, the binormal vector is defined as the cross product of the tangent vector and normal vector. It's called binormal. definition is defined as, okay, BT equals tangent vector cross normal vector. Okay, what does the binormal vector matter? Okay, what does this binormal vector matters? Okay, the binormal vector matters. Actually, you see, the tangent vector and normal vector lies in a plane, Okay, lies in a plane, because they are perpendicular, and this binormal vector tells how the direction of this plane actually changes. Okay, changes. So, for instance, if we're talking about the helix, maybe we just start with arbitrary curve. So suppose we have a curve. Now we find the normal direction is tangent direction, and then we find its normal direction, nt. Okay, now then we find the binormal direction. How do we find the binormal direction? Well, we do the following. Okay, find the direction that is perpendicular to this surface, perpendicular to the plane, determined by Tn and the normal vector, tangent vector and normal vector. Okay, it looks like this if we plot it. Okay. Okay, the binormal vector. Okay, this is BT. Let me plot that thing in red. BT in red. Okay. Okay. Use right-hand rule. Okay, use right-hand rule to find BT. Okay. You see, BT actually tells us how locally the plane determined by the thing changes. Okay. They find the normal direction of this plane. Okay. So BT, the binormal vector, tells us the normal direction of the plane determined by tangent vector and normal vector. Okay. Okay. Now here we have a frame. Tangent vector, normal vector, and a binormal vector. Okay, this is a frame. As the parameter t varies, changes, so we get a frame that moving along the curve. Okay, so as the parameter t varies, then we get a moving frame along the curve. Okay, now if we use parameter s, then this moving frame, is determined uniquely for this curve. Okay, for this curve. Actually, we know this actually totally determine the curve if we know the three parameters, the frame. Okay, i.e., if we have this frame of this curve, okay, we can determine the curve. Almost the total information, except you can do translation and rotation. Sorry, except you can do translate this curve. You translate this curve by a vector. So this still have the same tangent vector. They still have the same normal vector and binormal vector. Okay, so we can determine up the curve up to certain translation. So almost all the information. The reason is this is looks like the fundamental theorem of calculus. Remember, if we know derivative of a function, okay, we can determine the function up to a constant. Okay, a constant. A constant is simply just a translation in one dimension. Okay, a constant is translation in one dimension. I.e., we determine the function up to translation in one-dimensional case. Now, in the three-dimensional case, we determine the curve up to translation in R3. Okay, so let me do a remark. As the parameter t varies, we obtain a moving frame. Okay, so you see here, this is essentially the fundamental theorem of calculus. Okay, applies here. Fundamental theorem of calculus is we have lots of problems. Given a function, how to find its derivative. Given a function, how to find its antiderivative. Similar thing happens here. If I give you a moving frame, how do you tell me the curve? Okay, how do you tell me the curve? And if I give you a curve, how do you determine its moving frame? Okay, so this is actually an important tool in differential geometry. So remark, what kind of geometric property can we tell of this curve? Okay, by a moving frame. The moving frame. For instance, one important quantity of a curve is the curvature of this curve. Okay. Now, because we determine the curve up to translation, essentially we should determine the curvature of this curve by the moving frame. Okay, by this moving frame. I.e., if we locally know how the frame changes with respect to the parameter t, then essentially we should know the curvature of this curve, okay, at the t. Okay, so the moving frame method, although I did not explain what it is exactly, is an important tool in differential geometry. Exactly like the fundamental theorem, it plays the role of fundamental theorem of calculus in calculus 1 or 2. Differential geometry. Let me explain a little bit about differential geometry. Differential geometry is actually, in short, we just use calculus tools to study the geometric shape of certain things. Okay, curves, surfaces, higher dimensional surfaces, etc., etc. Okay, use calculus. Okay, calculus tools to study geometry. Okay, let's maybe now we have a lot of material. Probably cannot finish today. As I explained, a lot of properties can be read from the moving frame, how the three vectors changes with respect to the parameter. For instance, how do we determine the curvature? Yes, we can definitely define and determine the curvature by this frame. Let's see maybe one example. How to compute. Let's first give one example how to compute the frame. Okay, and then next time we will actually talk about how we define the curvature by this moving frame. Okay, let's do one example. A moving frame. Example. Okay. Let's see this example. Suppose RT is cosine Ti plus sine Tj plus Tk. let me find tangent vector, normal vector, and a binormal vector. Okay, so remember, tangent vector is just we find the unit vector of the derivative of position vector. So we find our derivative. We see we get negative sign, cosine, and 1. So this, what we are doing is actually the helix, okay, helix. Our derivative at t, norm, we already know this. The norm is actually, you find its norm, negative sine t squared, cosine t squared, plus 1 squared. So this is actually square root of 2. Sine squared plus cosine squared is 1. Okay. Then we divide by the norm. Divide by the norm, then we get a unit vector, which gives us the tangent vector. So this t, capital T, tangent vector, unit tangent vector will be derivative over its norm. So this will be derivative, the norm is 1 over root 2. Okay, now the derivative will be this thing. So this will be negative sine t, cosine t, 1. Okay, now what is the normal direction? The normal direction. The normal direction we need to find. The normal direction tells us how tangent direction changes. Is tangent take derivative over its norm. Okay, so this you get 1 over root 2. This is easy here. So this we get, what do we get? Okay, let's see. Okay, so t derivative, capital T derivative, this will be 1 over root 2. Negative sign, we get a negative cosine. Cosine, we get a negative sign. 1, we get a 0 if we take derivative. Then the norm, if you normalize it, so you find this is actually 1 over root 2. So, so we get a normal vector should be 1 over square root canceled. So we get a negative cosine, negative sign, 0. Okay, 0. Okay. So you see the normal vector has no z component. Z component is 0. So this means a helix. Okay, a helix. The normal direction is actually pointing towards to the horizontal. Okay, horizontal. Maybe let me plot in. Maybe use in color in red. Okay, so it's normal direction. Okay, just change direction. As this helix moves upward, so the normal direction, pointing towards to the center, horizontally. Okay, horizontally. Of course, what I just plotted is not the length is that's little issue. It's unit length. Okay, unit length. And then we find the normal vector. Okay, the normal vector and a binormal vector. So we get a normal vector will be t derivative, capital T derivative over its norm. So this will be negative cosine, negative sine, and z component is 0. Okay, and then binormal vector. Binormal, remember, bt is tangent cross product with normal. So get a binormal. Okay, so this will be, now tangent is 1 over root 2. So we use cross product ijk. So the tangent has a factor 1 over root 2. And then let's see what we get. Tangent vector. Okay, tangent vector. See, we have T, capital T. And then we plug in. Okay, plug in capital T in the determinant. Plug in normal in the determinant. Okay, so we have normal. Okay, and then plug in the determinant to find the binormal vector. Okay, so this will be negative sine t, cosine t, 1. And this will be negative cosine t, negative sine t, 0. Okay, so the binormal will be okay. Okay, let's compute the binormal. Okay, let's compute the binormal. Okay. Okay, the binormal vector should be, let's compute it. This is 1 over square root 2. Now the component I is cosine t 1, negative sine t 0, minus g, okay, negative sine t 0, 1, negative cosine. Now key plus key. Key, this is a negative sine, cosine, negative cosine. Okay, so we get this is 1 over root 2. This is negative sine minus negative sine, so sine t I. This is actually we get a minus cosine tg. Okay, minus cosine tg. And then this is a k times sine squared minus cosine squared. So sine squared plus cosine squared is actually 1. Okay, sine squared plus cosine squared, we get 1. So this will be the binormal vector bt. So we got bt in this case is 1 over root 2 sine t negative cosine t on 1. Okay, then we are done with this binormal vector for this. Okay, we have 4 minutes. Okay, okay, probably we don't have enough time to for another topic, to start another topic. Okay, okay, let me stop here for today, and next time we will determine the curvature of a curve using the moving frame method. Okay, giving a moving frame, always find the curvature of a curve by some technique. Okay.